All right, hi Science 10. So what I'd like to do today is first off go over the answers to the worksheet, and then secondly I'll cover the next section, which looks at half-life. Okay. Um, so here we have the three types of decay that we looked at: alpha, beta, and gamma. And so remember they had to do with materials that are radioactive, and basically because they're radioactive, the nucleus is unstable and it ends up splitting, and these are some of the things that get produced in that splitting process. And so here these are characteristics uh, of the three types of decay that we looked at. So we went through the symbols. So the charge of 0 would be the gamma, -1 is beta. That's another word for beta is electron. Charge of +2 is alpha, or helium isotope. And so alpha is the helium, beta is the high speed electron, and then this is gamma. Remember, gamma is the ray. It's not actually a particle, so it has no mass. Decay emitted from beta decay is a beta particle. There's the alpha particle stopped by aluminum foil. And this has to do with the penetration levels. That's beta. Gamma. And you might have had a hard time finding. So because both of these have the mass and they have charge, they get affected by both of these type of fields. Whereas the gamma, because it doesn't have the mass and it doesn't have the charge, it does not. So what we're talking about here, when we say it's affected, what we call this is deflection, where you have sort of a charged particle traveling through space, and then it basically changes its trajectory. It's kind of like how a golf ball behaves when it's in the air, right? So you have that type of deflection that's occurring. High energy wave with short wavelengths, that would be a gamma ray. And it has the highest form of energy of EM radiation. So EM radiation would include things like radio waves, infrared waves. Low penetrating power would be the alpha, so it can't really, it can be blocked quite easily, whereas the highest penetrating power is the gamma. Okay, so this is why, like, when you're storing nuclear waste, it needs to be in some type of lead or concrete casing. And what you worry about is any type of seepage, because if that nuclear waste gets into soil, it gets into water systems, it can be quite damaging for anything that encounters that, so like wildlife or humans. The next page, we looked at the reactions. Okay, so there was a typo on one of the questions here I'll get to as well. So we did some of these. So basically, in order for you to figure out which type of decay reaction it is, you just have to see what's produced. So if it's helium, which can be written like this or like that, then it's alpha decay. If you see one of these, it's gamma, and then beta is E for electron, or beta here, the beta symbol. Okay, they're the same. Again, what you're trying to do is make sure the numbers on the top on both sides are the same. So like here you got 234, here you have 230 and 4, so that adds up to 234. 91 here, 89 and 2 add up to 91. And then how you go about finding what element it is you look at the number on the bottom, because that represents the atomic number, which is also the number of protons, and that's how the periodic table is arranged. So if you look at number 89, that will be element AC. And like I said, there was a mistake, and that was on question 12. The mistake was that the symbols here had the wrong atomic number. So Ra should be 88. Okay, so again, the atomic number is the number of protons, and that's fixed. It doesn't matter which isotope you have, it should always have 88 as the number of protons for Ra. And then Rn should always be 86, not 26. Okay, and so this, so you might not have been able to do this because of the numbers there. But again, an element always has the same atomic number. It doesn't matter which isotope. And remember, what makes it something an isotope is when you have varying mass numbers. Okay, so the mass number is the one on the top, which is equal to the number of protons plus the number of neutrons. So it's the number of neutrons that's fluctuating. Okay. And then again, for the gamma, you see this little star here, which basically says you have an excess of energy in the nucleus that needs to be evacuated, and that's what the gamma ray is doing. It's getting rid of that excess of energy. So you end up having the same isotope that you started with. You just are able to remove that excess of energy. Now, these aren't the only type of nuclear reactions. We'll look at other ones, so they don't have to involve these particular particles. There's lots of other types of particles that can be emitted. Okay, so we'll get to that for Monday's class. So what I want to look at for today is half-life. So I'll go through some of the answers on this worksheet, and I'll have you complete the remainder on your own. Okay, so half-life, it has to do with how much time it takes for half a material to decay. Okay, so that means, so half-life, as the word implies, is half. So when you start with something, and I'll kind of explain what this means. I'll look at this chart here. So the parent isotope is the original isotope you're starting with. Okay, so at half-life of 0, so that refers to time 0, you would have 100% of your parent isotope, and you would have 0% of what we call a daughter isotope. Okay, so the parent isotope is the original isotope. The daughter isotope is what the original isotope decays into. So for example, uranium often decays into lead. Okay, so uranium would be the parent, lead would be the decay product or the daughter isotope. So this is at your time 0. Now after one half-life, what happens is we started with 100%, and now we have 50% of the original isotope remaining, and we have 50% of the daughter isotope being produced. Okay, so the number here always has to add up to 100. Now, if we're talking about mass, let's say we started with 10 grams, then here you'd have 5 grams. Okay, so half of what you started with has decayed. And when we say it's decayed, that means it's been converted into something else, in this case, what we call the daughter isotope. Okay, now, what's the time frame for the half-life? So every isotope, every radioactive isotope has its own specific half-life. It can be in fractions of a second, and it can vary to thousands and thousands of years, right? And everything in between. So the half-life, that's the actual time that we're talking about, differs for each type of isotope, and we'll get to some questions like that. After the second isotope, half-life, now you've got half of 50, so you have 25%. And so here, what's going to happen is it's at 75%. Okay, so you can see the numbers always add up to 100. Okay, and then you've got 12.5%. Okay, and you've got 87.5%. Right, I think that adds up to 100. And then here you're going to have 6.25%, and then this is going to be 93.75%. Okay. Now, if we were to put this on a graph, and I'll get to the graph in just a moment here, what the graph is basically going to look like if we talk about the parent isotope starting with 100% and working your way down, it's going to be this type of curve, and that's what we call a decay curve. And the thing is, this is never going to get to 0 because you can always divide a number by 2, right? You'll never end up getting to actually 0, but it gets pretty low where you can assume it's pretty much nil. So here, let's look at number 3. So a rock sample contains 120 grams of an isotope, and it has a half-life of 5 years. Okay, so for this particular isotope, the actual half-life time is 5 years. So what that tells you is every 5 years, you lose half of the original isotope. Okay, so if you were to start at time 0, you would have your full 120 grams. and then after 5 years, which represents one half-life, you now have 60 grams, right? And then you just keep dividing by 2. What half of 7.5? So that's going to be 0.5, 3.75 grams. Okay. Okay, and so it says how much of the radioactive isotope is left after 25 years. So there's only so after 25 years, because you've gone through 5 half-lives, you only have 3.75 grams. Okay, how many half-lives have passed if there's only 15 grams of the parent isotope left? So that would be after 3. And then how many years have passed if there's 7.5 grams? So that would be 20 years. Okay. Okay, so this one here, I'm going to get you to draw the curve. Okay, and I'll show you what the let's go to the next page and I'll show you what the curve, the last page I think has a curve, so we'll get to that and I'll explain how to do that one. Okay, so we can use percents. If we're given the mass, we can use the mass, and we can also use fractions. Okay, so here you've got a half-life that's 10 minutes. So again, half-lives vary for particular isotopes from, like I said, from fractions of a second to thousands of years. At UBC, they have a place called Triumph that basically produces particular isotopes for medical purposes and sends those directly to UBC Hospital for certain types of medical procedures. And so these are the reason why it has to be done like that is because these are things that have low half-lives, and so they can't be stored for a long period of time. So they have to be kind of manufactured and then utilized. So again, a half-life is referring to something that's radioactive, which means it's unstable, which means it's going to break apart, okay, at the nucleus itself. And so the half-life is looking at how long does it take for half of that substance to decay. Okay, so in this particular question is 10 minutes. So what fraction of the parent isotope will be left after 30 minutes? So what you have to look at is if the half-life is 10 minutes and you're talking about 30 minutes, that's going to be 3 half-lives. So the way you can look at this is you can say, okay, I'm going to start with, instead of 100% because we're using fractions, I'm going to start with 1, right? 1 over 1. After 10 minutes, okay, so the first half-life, so now instead of having 1, you've got 1/2, right? After the second 10 minutes, now instead of 1/2, which is 50%, you've got 1/4, right, which is 20%, 25%. And then after an additional 10 minutes, what you have here is 1 over 8. So the fraction of the parent isotope that's left is 1 over 8. Okay, and then after 40 minutes, so that's an additional 10 minutes, you're going to have 1 over 16. Okay, so a 16th. What fraction of the daughter isotope will be present after 20 minutes? So after 20 minutes, you have 1/4 of the parent isotope. So if you have 1/4 of the parent isotope, that means you're going to have 3/4 of the daughter isotope, right? So just like with the percentages that have to add up to 100, the fractions have to add up to 1. Okay, and then it says what percent of the daughter isotope will be left after 50 minutes. So again, if we just extend this, after 40 minutes, it's 1/16. After 15 minutes, or 50 minutes, it's 1 over 32. So that's going to be 31 over 32, okay, of the daughter isotope. Okay, so let's look at a graph. So again, this one here, let's do this one. Okay, so this is a decay curve. So here you can have it in terms of time. So in days, minutes, seconds, years, whatever time frame you're looking at, or you can have this in half-lives. Okay, and then here on the vertical, you can have mass, or you can have fraction, or you can have percentages, right? So instead of here, this would when you have your full parent isotope, this would correspond to 100%. So the decay curves can have different things on each axis, but the curve itself will look the same. So what you're doing after each half-life is you're dividing by 2. And so that's why you get this type of curve. Again, this bottom part here will never touch 0 because you can keep dividing a number by 2 infinitely. So it says, what is the half-life of the isotope? So if you started with 80 grams, after your first half-life, that should get you to 40 grams, right? Because 40 is half of 80. So what you want to do is look at 40, and that's right here where the curve is, and then go down to what time that represents. So that is 2 days. Okay, so what that's telling you is every 2 days, you're going to lose half of the original substance. Okay, and then it says how much of the parent isotope remains after 4 days. So here's 4 days, and then you go up here, and that corresponds to 20 grams. Okay, how much of the daughter isotope is present after 6 days? So after 6 days, we're over here, which is 10 grams of the parent isotope, which means we would have 70 grams of the daughter isotope. Again, the parent isotope is decaying into what we call the daughter isotope. What fraction of the parent isotope remains after 8 days? So at 8 days, we're right here, which corresponds to 5. So this is 5 over the 80 we started with. And so if you put that as a common denominator, or sorry, if you put that in lowest terms, divide both of these by 5, that's going to be 1 over 16. Okay, and then E, how long does it take for the parent isotope to decay to 5 grams? So again, this is where you are at 5 grams, so that took 8 days. Okay, so try to do the remainder of the worksheet, and if there's a particular question that is confusing or doesn't make sense and you need a little assistance on that, just send me a message and I'll get back to you and help you with that. Okay, so I like what I'm seeing from most of you, so just continue getting things submitted. Like I said, the take-home exam was for marks, and so I am using this for your overall final grade. And like I said, I'll be giving you a take-home quiz for the radiation materials that we've been looking at. I've got one other topic I'm going to cover on Monday, and then on Thursday I'll give you the take-home quiz for that. Okay, so and it'll just be based on what we're doing here. Okay, so anything that's not making sense, just please ask, and so I'll begin next class by going over the answers to the sheet here, and then looking at the next topic. Okay, so again, be safe, look after yourself, and I'll talk to you again on Monday. Okay, bye now.